Alright, today we're going to go over our acceleration review. Number one, what does the slope of a position versus time graph represent? Well, the slope represents the velocity. Slope is rise over run. The rise on a position time graph is your position in meters. The run is your time in seconds. So rise over run, meters over seconds, that's our velocity. Slope of a velocity versus time graph is acceleration. And using the same process, slope is rise over run, while our rise is velocity, which is meters per second. Our run is time, which is seconds, and we get meters per second, which is the unit of acceleration. Give an example of an object with a positive acceleration, but a decreasing speed. Okay, well here, let's say a rocket coming to rest on a landing platform. It is moving downwards, it's moving in the negative direction. It's slowing down, that's that decreasing speed, but that positive acceleration, since it's moving in the negative direction, it has a negative velocity, that means it must have a positive acceleration to actually be slowing down. So any object that's moving in the negative direction would have a decreasing speed as long as it has a positive acceleration. If an object is moving to the left and getting faster, what direction is the acceleration? For these, the way that I always go about it is there's really 4 different possible combinations. Velocity and acceleration, they're both vectors, they have a direction. You could have a positive velocity, a positive acceleration. You could have a negative velocity and a negative acceleration. You could have a positive velocity and a negative acceleration, or you could have a negative velocity along with a positive acceleration. And as it turns out, when your velocity and acceleration point in the same direction, you will always speed up. A positive velocity with a positive acceleration will become more positive. A negative velocity with a negative acceleration will become more negative. But when the velocity and acceleration are opposite, you will always slow down. If you have a positive velocity and a negative acceleration, well, your velocity is going to get closer to 0. And if you have a negative velocity and a positive acceleration, again, your velocity will get progressively closer to 0. So we know we're getting faster. This means the velocity and the acceleration have to point the same direction. So if the object is moving to the left, since we have a negative velocity, and the acceleration must be in the same direction, we must have a negative acceleration. So that would be leftwards. Now you might say, well, why is down not an answer here? Well, that's because we're always just dealing with either purely horizontal motion, left and right, or purely vertical, up and down. So even though down is a negative direction, we're not dealing with vertical motion here, right? The object's moving to the left, so we're only looking at that horizontal motion. Number 5, if an object is moving right and getting slower, what is the direction of acceleration? Okay, the object is moving right. That means we have a positive velocity. Getting slower means we have opposite velocity and acceleration. So a positive velocity, we must have a negative acceleration. So our acceleration here is left. Fully describe an example of an object with a 0 instantaneous velocity that has a non-zero acceleration. Okay, well, a ball tossed upwards will be accelerating downwards. Even when the ball briefly comes to rest at the top of its motion. If you think about it, if you're throwing a ball upwards, it starts off moving pretty fast upwards, and then it slows down, briefly comes to a stop at the top, and then it starts to speed up on the way down. Let's make sure we're still recording. Excellent. Must a slow-moving object also have a small acceleration? No. Use an example to explain. Well, if you are, say, moving really slow, you could be changing direction at a really rapid pace. Or maybe you are just starting, say you're in a car, and the light's green, you slam on the gas, and you have a really large acceleration, but you're not yet moving very fast. So a car at rest can have a very large acceleration if they slam on the gas to start moving. Draw a dot diagram of an object moving to the right at a constant speed. Okay. Dot diagrams are just a dot every second, or really a dot in some equal amount of time. So if we're moving at a constant speed, that means our object, represented by the dots, should travel the same distance in the same amount of time. So all our dots should be evenly spaced. And I'm trying my best here to get our dots as evenly spaced as possible. Here's our start. We're moving to the right at a constant speed. Now let's do moving to the right, getting faster. If we're getting faster, the object should be traveling greater and greater distances with each dot. So you can see at the start, we're not going very far in every interval of time. But later on, as we're moving more to the right, we're traveling a larger and larger distance. Now, we're moving to the left and getting slower. Okay, so let's start on the right. Here we are. If we're getting slower, we must start out really fast. Really fast should be really far apart. We're traveling a great distance in our amount of time. Gradually, oh, don't mind my dog. Gradually, we're traveling less and less distance. What direction is the acceleration for questions 7 and 8? I'm not quite sure if we meant 7 and 8. Maybe I have an old version of the review here. But let's go over 9 and 10. Let's talk about these directions of acceleration. Well, we're moving to the right, getting faster. So the velocity is positive. We're getting faster. The acceleration has to match our velocity. So we have a positive acceleration. Number 10, the object's moving to the left, negative velocity. Getting slower means we should have the opposite sign acceleration as we do velocity. So we would also have a positive acceleration. It's very important. Positive acceleration does not always mean speeding up, and negative acceleration does not always mean slowing down. It's dependent on which way the object is moving. Alright, let's continue with some graphing. Sketch a position and velocity time graph that represents the following situations. Objects starting from rest, moving forwards, and getting faster. Alright, we're going to run through these. Highly recommend reviewing your notes if needed. I will be talking about each situation. Here, if we're starting from rest, moving forward, and getting faster, the starting position is plus 10 meters. So let's say maybe we're starting up here. This is 10 meters. We're starting at rest, so we're flat. Then we're moving forward and we're getting faster. Moving forward and getting faster looks like this. On a velocity time graph, we're starting from rest. So let me draw this in purple so you can see it a bit better. At rest on a velocity time graph is on the x-axis. And then we're moving forward, getting faster. Our velocity time graphs won't curve. We have a constant acceleration, so that slope should be constant, since the slope of a velocity time graph is our acceleration. And we should end up in our positive territory, since we're moving forward. Car driving at a constant speed. Alright, starting position of 0. Well, here's 0 meters. Constant speed on a position time graph looks like this. Constant speed on a velocity time graph looks like this. C, a car starting from rest, moving backward while getting faster. All right, so again, we're at rest. The starting position is 0. Here's our rest. Let's do this in purple, just to make sure we get it and we can see it starting at rest. Moving backwards, getting faster. We're still getting faster, so our slope should still be getting steeper, because our slope on a position time graph is our velocity. Let's draw in our starting at rest again, starting on the x-axis. And now, really the way we tell how fast something is moving on a velocity time graph is we look at the distance away from the x-axis. And we see that here, our line, it's getting further away from the x-axis. That means we're speeding up. Same thing that we had. Oh, looks like I accidentally deleted one of those. But up here, we're moving away from the x-axis. That's getting faster. All right, a car coming to a stop. The starting position is 0 meters. Okay. We don't know what way the car is moving, but let's just presume we're moving forward. So we're moving fast. Don't want a straight line. We're moving fast. We have a steep slope, and then we're leveling off. There we go. Coming to a stop where we have 0 slope at the end. We're moving forward. So we have a positive starting velocity, but we're slowing down. Eventually, we need to end up at our x-axis because we will eventually come to a rest. And a rest on a velocity time graph must be the x-axis, where we have 0 velocity. Excellent. A car in reverse slowing to a stop at the end of a driveway. We're starting at plus 10 meters. Let's say 10 meters is up here. Slowing to a stop at the end of the driveway, so we're moving backwards. That means we're moving down on our position time graph. We're slowing to a stop at the end of the driveway. We can say the end of the driveway is our origin there, our position of 0. Okay, now our velocity time graph. We're moving backwards. We're slowing down. Well, moving backwards means we need to be in this negative territory beneath the x-axis. And we need to get closer to 0. And 0 velocity on our velocity time graph is, of course, represented by that x-axis. Okay. 13. Sketch position versus time and velocity versus time graphs for the following situation. You hop on your bike and accelerate gradually for 5 seconds, then travel at a constant velocity for the next 10 seconds. At this point, a car swerves in front of you, and you quickly stop yourself. Okay. So let's do this in little bits. Let's start off with 5 seconds. You hop on your bike and accelerate gradually for 5 seconds. Okay. Accelerating gradually. Looks like this. We're getting steeper. We're speeding up. Then you travel at a constant velocity for the next 10 seconds. I may have made my graph a bit too steep. Let's make it less steep so we can actually maintain this velocity. There we are. Because now, if we're going all the way out to 15 seconds, we need to keep this a straight line. Like so. Now at this point, a car swerves in front of you and you quickly stop yourself. So we will change our slope gradually to 0. We come to a stop. We sped up moving forward, we moved at a constant velocity, and then we're slowing down to a stop. Let's translate that down into our velocity time graph. Well, we're speeding up moving forward. This looks something like this on our velocity time graph, right? Our velocity is becoming more and more positive. Then, for 10 seconds, our velocity just stays constant. It's not increasing, it's not decreasing, it's just constant. And then, we slow down to a stop. Our stop is that 0 velocity. Alrighty, excellent. Looking at our next section, we're going to get into this position versus time graph. Excellent. Which car is faster, car 1 or car 2? Well, on a position versus time graph, as a reminder, slope is the velocity. So whichever one is steeper is the one that's moving the fastest. We can also tell, well, car 2, the red one, it's moving a greater distance over the same amount of time as the blue car, so it must be moving faster. So car 2 is faster. What is the velocity of car 1? Well, We just said slope is the velocity. So find the slope of car 1. How do you do this? Well, you just can do rise over run, or you could do y2 minus y1 over x2 minus x1. The key is you have to pick 2 points. Car 1 starts at 0, 0. That will be one of my points. And let's find something easy. Right here, this lines up nicely with our grid. So let's do our 2 points. One of them being 0, 0, and the other one being 5, 10. Excellent. Okay, so our y2 is 10. Our y1 is 0. Our x2 is 5. And our x2, pardon me, is 0. This gives us, nice and simple, 10 over 5, or in other words, 2. We know the slope is our velocity, so this is 2 meters per second. How far did car 3 travel in 8 seconds? Well, car 3 is our green. In 8 seconds, it started out all the way over here at 0 for our position. It ends up here, 20 meters. So in those 8 seconds, it must have traveled 20 meters. At what time does car 3 pass car 1? Well, car 1 is our blue. So this is moving along right here. Car 3 is our green. We can see they end up at the same position 6 seconds in, and afterwards, car 3, the green, overtakes car 1, the blue. So 6 seconds is when that happens, when they're at the same location when car 3 passes car 1. What would the velocity time graph look like for each car? Draw them color-coded, okay? Let's see. I may have to find a red, but let's start off with the colors that I do have. I have this darker green. Let's do car 3. This position time graph shows us it is not a constant slope. The slope gets steeper. It's speeding up. It must be accelerating. So for green, we know that velocity is increasing as time goes on. Let's look at another one. Our blue, I have blue. There's a constant slope. On a position time graph, constant slope is a constant velocity. So blue maybe has some velocity like this. Oh, let's get that as a straight line. Looks like my pen is having some difficulties. There we go. Blue might start out faster than green, but green eventually is going faster. And then lastly, let's go ahead and grab a red. Red is moving faster than blue. It's steeper, so it must be at some faster constant velocity that we can draw in like this. But even still, eventually, green is going to be going faster. It hasn't quite caught up. But if you imagine extending this graph so that we go for more than 8 seconds, eventually, green is going to surpass red. Okay. Alright, number 19. Label what is happening along each segment of the journey below. For each segment, you should indicate A, motion or no motion, B, the direction of travel, C, is the motion constant, increasing, or decreasing, and the direction of acceleration. Alright, let's go ahead and do this. So for segment A, well, let's start off, motion or no motion. There is motion. The car is moving. The direction of travel, they have a positive velocity. They're moving forward, the way we tell. Well, on a position time graph, you're looking at the slope. Slope tells you if the velocity is positive or negative, if they're moving fast or slow, and if they're speeding up or slowing down. So here they have a positive velocity. The motion is constant because the slope is constant. Slope is the velocity, so the slope is constant means the velocity is constant. And direction of acceleration, well, there is no acceleration because it's undergoing constant velocity motion. Segment B, now we have a curve. Curves mean there's some acceleration going on. The object is moving. Their position changes with time. They are moving forward. Their position becomes more positive as time goes on. They are slowing down. We tell because the slope gets less steep. The steeper the slope, the faster the motion. So if your slope gets less steep, you're going slower. And the direction of acceleration would be negative. You're moving forward, slowing down. This is a negative acceleration. Section C. There is no motion here. Well, there's no motion, so we don't have to do part B. C, we're not increasing speed, we're not decreasing speed, and we're not even at a constant speed, we're not moving. And D, again, we don't have to do that. There's just no motion at C. But for section D, here we are moving. There is motion. We have a positive velocity, we're moving forward. Since the line is getting steeper, we are speeding up. And we have a positive acceleration. Moving forward, speeding up means positive acceleration. Okay. E. Here, we are moving. There is motion. We are still moving forward because we have a positive slope. The slope is getting less steep, so we are slowing down. And moving forward, slowing down, is a negative acceleration, just like we had in segment B. Our last two segments here, F and G. Let's start with F. There is indeed motion. This time, we're moving backwards because we have a negative slope. Negative slope means you're moving backwards in that negative direction. We are speeding up. Even though we're going down on the graph, we're speeding up just because speed, you can tell from the steepness. The line's getting steeper, so we're going faster. Moving backwards, speeding up, is a negative acceleration. And for G, there is motion. We are moving. The slope is negative, so we're moving backwards. We are at a constant velocity since the slope does not change. And we have no acceleration. Alright, our last section, part 3. These are our kinematic problems. These are the ones with our equations. Keep in mind, you will be expected to use these equations. You will also be provided the equation, so there's no need to memorize them. But for completion, let's go ahead and write these equations right here. We know we have delta x is equal to our initial velocity times time plus 1/2 the acceleration times time squared. We also have our final velocity squared equals the initial velocity squared plus 2a times our delta x. And lastly, we have our final velocity equals the initial velocity plus acceleration times time. Alright. Our process here is always going to be writing down our givens, writing down our unknown, and then figuring out what equation we're going to use. So let's go ahead and start off. You start from rest. This is a key. That means your initial velocity is 0. As you're solving these problems, make sure you always show your work, because you're gonna get points just for showing your equation and your work and your givens. So make sure you're always writing all this stuff down so we can give you as many partial points as possible. We know the acceleration is 5 meters per second squared, and the time we're given is 10 seconds. Okay, we have our givens. What are we solving for? Well, we're asked to calculate final velocity. So that's something we don't know. We have our 3 givens, we have our unknown. Let's find an equation that has all these variables in it. It looks like our last equation is going to be the one we want to go for. So let's write it out without plugging anything in. Now we can go ahead and substitute in our variables and solve. Final velocity. We know that the initial velocity is 0, so that just drops out. 5 meters per second squared multiplied by our 10 seconds our seconds cancels one of our seconds right here. So we end up with the final velocity is 5 times 10 meters per second. Alright, number 21. You're driving your car at 9 meters a second. Alright, let's write that down. It's an initial velocity. 9 meters a second. You increase your speed with a constant acceleration of 10 meters a second squared. Up to 35 meters per second. That's our final velocity. Calculate the distance you travel. Okay, based on this information, let's pick out our equation. We don't have a time, so we're going to go ahead and use this middle equation. Let's write it down. And now we'll go ahead and solve. Make sure when you're squaring your units, the numerator and the denominator, they both get squared. So we get meters squared per second squared here. And we'll go ahead and subtract 81 from both sides. This is going to get us 1,144 meters squared per second squared is equal to 20 meters per second squared times our displacement. Go ahead and divide by your 20. We can even write this out. This cancels, and then we get all of this to cancel. We have 1 meters left. Go ahead and do our division, and we end up with our displacement being 57.2 meters. Alright, number 22. Looks like this is our last problem. Bikers traveling at a constant speed of 8 meters a second for 7 seconds. They see a penny on the road and slam on their brakes. Biker measures their tire marks to be 3.6 meters long. Okay, calculate the time it took them to stop from the moment they began braking. Okay, well, and we get a little hint. We have to calculate the acceleration first. Let's see how we arrive at this conclusion without our hint. We know the distance they travel while they're braking. It's 3.6 meters. We know their initial velocity going into the brake is 8 meters a second. We know since they're braking to a stop, their final velocity is going to be 0. And now you can take all these variables and say, oh, calculate the time, right? We're looking for time. The problem is, if we don't have an acceleration, every single equation up here requires acceleration. They all have acceleration in them. So if we're looking for something that's not acceleration, and we don't have an acceleration, we always are going to need to solve for that acceleration first. So pick an equation that has these 3 variables and acceleration in it. And that's going to be the same equation that we just used. Let's go ahead and write that down. we'll plug in, just like last time. And solve. Divide both sides by your 7.2. We get a negative acceleration. And now that we have the acceleration, we can pick an equation to solve for our time. There are multiple options, but the easiest one is going to be the equation we have on the right. And that is final velocity equals initial plus acceleration times time. Plug in. Excuse me. And now we're just going to divide 8 meters per second by negative 8.9 meters per second squared. I did forget to make this negative, so the negatives are going to cancel. And we end up, if we do a little rounding, our time is 0.9 seconds. And there we have it. That's our final answer. Now let's go ahead and calculate the distance traveled during the ride. Well, we know there's really two different segments, two legs to this ride, if you will. There's the segment where he's slowing down, and we know that's 3.6 meters long. So let's go ahead and break it into two legs. We have our first leg, and we have our second leg. We know the second leg is 3.6 meters long. We know the total is just adding them up. So all we really need to do at this point is figure out how far the biker went when they were moving at a constant speed. Well, we do have an equation for constant velocity. This is from our previous unit, delta x equals velocity times time. Something I want to point out. Looking at this equation, the reason this works, when the acceleration is 0, take a look at this equation on the left. If your acceleration is 0, then this whole term turns into 0, and you just have displacement is velocity times time. Now, of course, if there is acceleration, you have to factor this in. But for the first leg of this drive, the biker is not accelerating. They're at a constant speed. So let's use velocity times time equal to our displacement. This is equal to velocity times time. Plug in that velocity, 8 meters a second, times 7 seconds. And this is really just doing 8 times 7. And we get 56 meters. Don't forget to add in your 3.6 of skidding to a stop. And that gives us a grand total, 56 plus 3.6, of 59.6 meters.